It's a program consists of 16 weeks with many plenary talks, mini courses, colloquium talks, and contributed talks. And also it will be accompanied by proceedings. So if you are interested to contribute a survey article or survey plus research article, it's very, very welcome. And also I highlight that the Fields Institute has a monograph series. So if on this topic, or I mean, for this program, it should be on this topic. If you plan to write something in the book series, it's about 150 pages to 200, usually in this category. So if you want to publish a monograph, it is very welcome by Fields Institute people. You can contribute. And I mean, attached to this program, it's already there are already at least one monograph, and there will be one or maybe two more. But I mean, people are open at Fields Institute, open to more contributions. So please think about it. We do not have really an opening ceremony because 16 different topics, and some people have registered for some weeks, not all of them. So the number of people in sessions will vary, I mean, up and down. However, we've decided to have a closing ceremony. So I think on December 13th, when we have our last colloquium talk, after that, we will have a closing ceremony, and we'll invite the Fields officials also to participate. So please mark in your calendar to attend that closing ceremony. I do not know if Damir and Ilya are with us, the other organizer. Damir, Ilya, they should be somewhere.
I'm here. Welcome, everybody.
Yeah. So I personally would like to thank both of them. I mean, Ilya and Damir both contributed a lot of time and energy to have this program, and also the Fields Institute colleagues, I mean, the program managers. Thanks to all of them. If you want to add anything, Damir or Ilya, please go ahead.
Well, I wanted, of course, to thank Javad for doing most of the organization and for hope that this experimental program will be a success. And I wish everybody a great programs. And Javad, thank you for being the force behind all this. Thank you.
Thank you indeed, and to all other colleagues who helped us. Well, without any delay, we can start the mini course. I apologize from experts which are in the audience, as I mentioned in my email exchanges. It's a very elementary topic that I've chosen to talk about. It's about representation theorem, and my goal was to prepare the graduate students for the upcoming plenary talks, and also other more specialized mini courses which are ahead of us. So please accept my apology, because you will see the talks are really, I mean, elementary on the representation theorems about Hardy spaces. And also, please do not hesitate to interrupt me if something is not clear, because it's a course. It's not a plenary talk. We are here to discuss some, I mean, well-known classical topics, and then so if anything is ambiguous or not clear enough, please stop me. I shared the abstract to see what is my goal. Do you see this PDF file?
Yes, sir.
Yeah.
Yes, we see.
Sure. So The representation theorem, or more precisely a representation by the Poisson integral, is the main goal. We want to know why a function f can be represented by an integral of Poisson kernel times another function. But to do so, we need to cook. We need to develop some materials to arrive this. That is why at the beginning, I talk about convolution and Young's inequality, and even more important than the previous two topics, approximate identities. Approximate identities is the core here, and it's a general topic, and based on that, the other things can be deduced. Two specific approximate identities which we are interested in are Poisson kernel and Fayet kernel. There are many, many more, but these two are interesting for us. The first one, Poisson kernel, gives us the representation theorem that we are looking for. And the second one, Fayet kernel, gives us polynomials and help us to obtain some interesting polynomials which approach to our function in the Hardy space setting, either in the norm or by other topologies. And it is interesting to know that even though for Hardy spaces, it is classical, it has been known for many, many years, the same topic, I mean, polynomial approximation in function spaces is a topic which is still very active. And in the past 2-3 days, with my colleague Thomas Ransford and Pierre Olivier, which is here with us, and some others, we have obtained results again about another classical space, the Dirichlet space. I mean, polynomial approximation with Dirichlet space was done with Fayet kernel, and it's fresh, brand new topic. And still there are open questions about them. I mean, in Dobranch-Wozniak spaces, if you are interested in. And then to set the stage, I will provide the definition of H infinity and H2. And for H2, I'll give 4 definitions, but of course, equivalent definition. And with each one of them, we'll look at the Hardy space H2 from a different angle. And some of them are good, not all of them. Some of them are good to generalize and obtain HP spaces. We will see some definitions. If you simply 2 by P, you obtain something else. You do not obtain a HP. And even in the upper half plane, when you place D by C plus, it's even more interesting. When you replace 2 by P, you do not obtain the Hardy spaces, which is in our mind. In upper half plane, we have at least 2 Hardy spaces. And then these 3 parts is just to have familiarity with Hardy spaces without giving, I mean, detailed proof. But from here up to the end, we talk about representations. And the first one, little h1 means harmonic. Many of these representation theorem work even in the harmonic setting. So we do a construction for little h1, and then all different types of convergence. Do we have uniform convergence? Do we have weak star convergence? Or convergence in LP, contrast to L infinity, which is here? Or weak star with respect to measure, or with respect to bounded. I mean, all these different type of topologies that we face, and we obtain different types of convergence too. So, and again, back to the both kernels that I chose before, if you choose Poisson kernel, you obtain some functions which goes to your original function, either uniformly or in LP or in some sort of weak star type of convergence. And if you use the Fayet kernels, you obtain polynomials which do the same job. So this is, I can say, is the heart of these mini courses, to see all these differences and what we can get with different kernels, in particular with those two kernels. And then more specialized, because our focus in on the Poisson representation, having these tools, we talk about different forms of Poisson representation. All the time, we see integral Poisson kernel, a function or measure, but they can have different interpretation and show different thing either in h of d bar, which means harmonic on something bigger than the open unit disk, or bounded harmonic function, HP, little hp, and or h1. And then pretty much everything goes from little h1 to capital H1. So all the tools that developed here for H infinity HP easily generalizes to capital HP. There is one difference, is for little h1. If we go from the representation that we have for little h1, if we go for capital H1, it is a representation, but it's not the whole truth. And a very, very deep and fundamental theorem is hidden here. The theorem, one of the rare theorems, which is by both brothers, Riesz brothers, F and M Riesz theorem, which allows us to say something more here. When we go from harmonic setting to analytic setting, we jump from a measure which represents our function to a function. And this big jump is something very, very important and fundamental in the theory of Hardy spaces. Many interesting books on this topic. I mean, the classical ones are books of Duren, Garnett, and Paul Kouzis. I mean, these are on these all aspects of Hardy spaces. Also, there is a book of Martinez and Rosenthal. It's on H2, just Hardy-Hilbert space. And that book is mostly about operators acting on this space, but it's a very interesting book. And we follow 6 in this. Let me show you what is 6. If I can find it. I think I have to go back to this, share the screen. Voila. I will follow pretty much this book, which is, I mean, published around 2010, 2011. And the topic says it all, I mean, representation theorem. It's not about all aspects of Hardy spaces, it's just about representation theorem. And I have summarized, I will share with you after the break in the chat part. I have summarized some of these in a PDF file. It's not in the final format, but still I can share it with you. About 40, 50 pages, concise treatment of what we want to do in coming days. So that is a brief explanation of what is our goal in these lectures. Any question by now? So if not, I go to OneNote. Where is my OneNote? I have to start this and then run OneNote. Well. hard spaces. Representation theorems. Oh. Sorry, I have two screens here. On my other screen, I opened the PDF file I mentioned, and based on that, we proceed. Okay, the first part, we want to be precise about what do we mean about boundary values. We stay in the open unit test, so even though the same thing, same topic can be explored in the upper half plane, but most of, pretty much everything, all the representation theorem will be about the open unit disk. At the end of that PDF file, there is a section which summarizes the representation theorem about upper half plane too. But now we stay in the open unit disk. And having a point zeta on the boundary, zeta here. Note that the function is defined inside. So f is defined for z, and z belongs to D. And what do we mean by lim of f of z, where z goes to zeta? And even sometimes we do not mention limit, we simply say f of z goes to a limit L. What does this mean? If with the first case, we do not put any restriction, so it means that the point Z is inside the T, so it's restriction is restricted to open unit disk, but it can approach to the point zeta in any manner it wishes. In this case, it's another formulation of the continuity. If we do not put any restriction, so I put number 1, no restriction. Of course, we stay inside T, of course. Z stays inside T. This is the definition of continuity, and if limit exists, if lim f of z exists, this is the same thing as f is continuous at the boundary point z. It's something strong. It's a very strong assumption to put on the function. Usually, even in this setting of Hardy spaces, usually this is not the case. We will see. Even H infinity functions, they are bounded. They are very nice at the boundary in a sense, but still we cannot put such a restriction. If this holds at all point of the boundary, we end up with something which is called the disk algebra. All these points on the boundary are nice point, and the function, even though initially is defined on D, can be extended to D bar as a continuous function and form a space which is the disk algebra. But if we go a bit further, we forget about this algebra. In a sense, this algebra is one of the smallest spaces that we consider. If we go for larger spaces, even larger could mean H infinity, larger than that HP, larger than that H1, which contains the HP for P between 1 and infinity. We cannot say this. This is a very heavy assumption. And so what we can do, we go the other way around. We put some restriction. This is one extreme. The other extreme, number 2, instead of letting the point Z to be free and go to zeta in any manner it wishes, the other extreme is to assume that zeta approaches Z on a radius. In this case, in other words, we study lim r goes to 1, and sometimes we emphasize by putting 1 minus here, which means that it's less than 1, f of r zeta. If this exists, we say that f has a radial limit at this point. And there are different notations. In more advanced treatment, we simply write f of zeta. You will see in coming weeks the PDF file of mini courses by, for example, I've seen Stefan Garcia notes, I've seen William Ross, and even Tom Ransford. They use this notation. But at the very beginning, to emphasize that there is a difference between the function inside disk and on the boundary, I use the F star. It's a bit cumbersome notation, but at least it tells us that it's something different. It's a function which lives on the boundary. So F is defined on D with values on C, but F star is defined on T. Of course, if the limit exists at all point, or at least almost everywhere. And we will see the interplay between these two functions and how the function space theory is related to harmonic analysis by despairing. So that's another extremity. I mean, the first one, we do not put any restriction. The second one, we assume the Z goes toward the boundary on a straight line on the radius. And now something in between, not the first one, which is kind of free, not the second one, which is so restricted. The third one, we assume that Z goes toward the boundary through an angle like this. So Z is restricted in this opening. And in this case, if the limit exists, let me go to that page. If the limit exists, we write it this way, lim f of Z, Z goes toward the boundary, and either we put it this way. If the limit exists, we say that f has a non-tangential limit. Non-tangential because places very close to the boundary from above or from below, these are forbidden. So no, the opening can be anything less than pi, but it's in a way, it's far from the boundary. That is why we call it a non-tangential approach region. And if the limit exists, we use the same notation as the case before. This is not a coincidence, because in the Hardy space theory, what is important is almost everywhere. And there is a theorem. Of course, if this limit exists, the radial one also exists. And there is a theorem we'll see probably even today, which says that almost everywhere, the limit non-tangential one exists. So we do not need to define a different notation. So we use the same notation for both of them. And as I said, when the lectures becomes more advanced, even F star is replaced by F of zeta. I mean, with the same notation that we use for the function. Up to here, it's enough for the Hardy space theory. But for Dirichlet spaces and some other spaces, we need other domains. That is why I give the definition of this opening. One way to do this is by this formula. Gamma, it depends on parameter C, but this domain is anchored as zeta, is defined as the set of all Z in the open unit disk, such that the distance between Z and zeta is controlled by the distance of Z to the boundary. 1 minus mod Z is the distance of Z to the boundary. So two distances are controlled. C is any parameter bigger than or equal to 1. If C is equal to 1, we recover the case 2. But what is more interesting for us is C bigger than 1, which means that we really have an opening like this. The bigger C is, the wider is our opening. And at most, when C goes to infinity, the opening becomes pi, but we do not go to, C is not equal to infinity. It means that it's not equal to pi. Another way to say the same thing is that if we put C equal to infinity, we recover case 1. So in a sense, these domains is a passage from case 2 to case 1, corresponding to the values of C going from 1 to infinity. C equal to 1 is the radial limit. C equal to infinity is the first one, no restriction. And we are interested in something in between. So up to here is enough for Hardy spaces, but we need more for other spaces. And that is why I also talk about non-tangential approach regions. How to define a tangential approach region? Consider the function phi of t equal to c times t for t bigger, and it's a line like this. For different value of c, we have different lines, so different c's. And the preceding definition can be rewritten as this one, can be written as gamma. Either you put it C or you can put it phi here of zeta is the set of points in the open unit disk such that the distance between Z and zeta is controlled by phi of the distance of Z to the boundary. It's the same thing, but I wrote it a bit differently. And now, why is this way of writing can help us? Because we can consider other functions. In particular, we are interested in functions such that the derivative here is infinity. Or in other words, it's tangential to the y-axis. For example, phi of t is equal to c root square of t. This is one of the functions I'm interested in. Or another one, this appears in studying Dirichlet spaces. Also this one, phi of t equal to a constant over log of 1 over t. As you see, both of them are tangential to the y-axis. You can even put the tangent line on the x-axis if you are more familiar with that. But what is the consequence? If, for example, if you use this if you use this one, the region you obtain are like this. So this is the open unit disk. This is the point zeta. And for different value of C, you obtain different disk here, which are all tangent to the point zeta, but stay inside the open unit disk. So all of these are disks with different value of C. And so in this way, if you use this phi, we allow Z to go towards zeta, but be close to the boundary. How close? It depends how tangential our phi is to the y-axis. This we can say is of degree 2, and this we can say is of degree exponential. In other words, this function is highly tangential to the boundary, but still it's not the complete freedom that we had before in case 1. We have a lot of freedom with this. We have a lot of freedom with this. It's infinitely tangential to the boundary when we go, but it still is not the full freedom. And this completes, so we can say that number 4, it's the same definition as we had for the tangential, but instead of C times 1 minus Z, I say gamma phi is defined as before. I say if lim Z goes to zeta, but Z belongs to one of these gamma phi of f of Z. If this exists, we say that it has it has tangential limit, but restricted to the domain gamma phi. So these are 4 types of the approach region that we consider. One thing that we need to consider, and it's important in application, it is true that, for example, in the non-tangential setting, we can have different opening. We can have an opening like this, or an opening like that, bigger and bigger. And eventually, I mean, if we consider all values of C, we can be as we wish, wider and wider. So this brings the, I mean, this wrong interpretation, a wrong conclusion that if this limit f of z, z goes to zeta, z belongs to gamma c, exists for all c bigger than or equal to 1, then we can make our approach region wider and wider as we wish, and eventually let C go to infinity. And therefore, and this is very dangerous, conclude that, therefore, if we take union with respect to all C, not like that, we can conclude that lim f of z, z goes to zeta, z in D exists. And why do we make such a conclusion? The conclusion is because the union of all gamma c, c bigger than or equal to 1, is equal to D. And that is why we anticipate to have something like this. But this is wrong. But this is wrong. No, even though the union is equal to D. And let's see why this is the case. And this is another manifestation of the fact that the epsilon delta definition one of the micros is on. Please set it off. Yeah. This also brings us to the point to appreciate the definition that we have either in analysis 1 or in calculus 1, the epsilon delta definition of the limit or the continuity. That if you look at the history of this, how this, the big analysts worked to arrive at this, it wasn't an easy process. It took time to arrive at this definition. And this is a point that we appreciate that definition and see why this is not true. What does this mean? Our original definition. This means that we fix, and fix is important. We fix C, so where was it? This one. We fix C bigger than 1. I see some comments in the chat. Where can I go and see them? I got some notification. Well, I think not the intersection, the union. If I said the intersection, I apologize. The union is equal to D because it becomes wider and wider. And the justification is here. We fix C bigger or even bigger than or equal to 1. And then what is the original definition of this, as we saw before? The original definition is L is the lim of f of z. Z goes to the boundary, but restricted to the gamma c is this. For every epsilon, there is a delta such that if the distance between z and zeta is less than delta and z stays in gamma c, then the distance between f and L is small. That is good. That is the definition. And to be able to compare, it's not clear where the difference comes from. But to be able to compare, if I write the definition of lim, z goes to zeta f of z equal to L, it's pretty much the same thing. For every epsilon, there exists a delta such that z minus zeta is less than delta, but z stays in D, and the same conclusion. It's very similar. And that is why this, bring us to this, wrong conclusion that if we consider all C's, therefore we could arrive at that conclusion. But the whole point is here. The whole point is here. There is delta, but delta depends on what? Well, the first thing which comes to mind is epsilon. Of course, it depends on epsilon. It depends on the function f, but for the time being, let's fix the function. What is important here is that delta depends on C too. That's the hidden part of it. Delta depends on C. And when you consider different C's, there is a possibility, and it really happens, that when C goes to infinity, then delta goes to infinity too, and that is why we cannot make this conclusion. So this is the intrinsic the difference between these type of approach region that we have. And that is why I wanted to emphasize the difference between tangential, non-tangential. I'm sorry, delta goes to 0. Thank you. Thank you, Lynn. Lynn mentioned my mistake. I said delta goes to infinity. Delta goes to 0. Indeed. Thank you. So we do not find a delta here, which just depends on epsilon to make that conclusion. So this finishes the part about approach region. Well, what was our goal? Let's emphasize what is our goal. The function z goes to 1 minus mod z squared, z minus zeta squared. This is called the Poisson kernel. And I'm sure you have seen many times a representation like this. F of z equals to 1 over 2 pi, integral 0 to pi. This kernel, z minus z squared. And then either a function here or a measure. Let's put a function phi. We'll mix with the function phi, which is about. So I put f star to indicate the boundary values. And then the m of zeta is the Lebesgue measure. What does this mean? This is our goal. Again, there is something in the chat. Please let me verify. Depraj asks, what is an example of a non-tangential convergence without, we'll arrive at it indeed. I mean, thank you. It was in my mind to mention some examples, two indeed. One of them is simple. The other one needs a bit more detail. I will mention this momentarily. Just mention my goal. This is the goal. We want to understand what does this integral representation mean? And I mean, given f, two procedures. The first one, f is given on D. And then the question, is there something on the boundary, I wrote f star, or a measure mu such that one holds? That's one question. So in this case, we start from something on D. And this is pretty much the essence of Hardy spaces because they are defined on the open unit disk as analytic functions. We want to see what happens if we go to the boundary. And then we obtain something on the boundary. Do we have a representation? This answers in detail this question. And the second one, we start from something on the boundary. So we start either, I use f star, even though it can be another function, but just to say that we are on the boundary. We start with f star or a measure or a function s or mu on the boundary, and then use one to define f on D. So we have the data on the boundary. We define a function f on D. And now what can we say about f, the properties of f? More specifically, what happens, I mean, we discussed the boundary behavior. when we go toward the boundary, what is the relation between this function and the one we started from the beginning? Please let me see what is in the chat again. Sheldon mentioned precisely one of my examples. Thank you, Sheldon. It's the singular inner function with produced by a Dirac measure at the point 1. But this is my example with some variation, and also an infinite Blaschke product, which needs a bit more detail. I think we are getting close to the post time, post cafe, though there's, I hope we were all together so that we can chat, but well, there's the online era. Sorry about that. So I stop here.